Alright, welcome back. This is chapter 3. It talks a lot about electric potential energy, voltage, distance, electric fields. It's a lot of, you're going to see the word potential a lot, maybe in every question almost. There's a lot of formulas, so we're going to start with that. But before the formulas, I'm going to start with question 1. Alright, because this is something you need to memorize. What is an equipotential surface? Very easy, and you need to know this. It's a definition. Basically, a surface where the electric potential is the same at every point, as the name suggests. Okay, this is a very important definition, and you must memorize it. And there are some characteristics that you need to know about the equipotential surface in case it does come. Okay, so the first one is this. This is the first point, that the electric potential is the same at every point. And there's a very important characteristic that basically says if a charge if a charge moves along, I'm gonna cut until I write it, okay? Alright, so basically if a charge moves along an equipotential surface, the work done by the electric field is equal to 0. Why? Now you're gonna see in the formula sheet that I'm gonna give you now in a sec, that W is equal to QV. Alright, and basically QV between 2 points. Now if you're on an equipotential surface, then the voltage between 2 points, A and B, the difference in voltage between them, when I say VAB, and the difference in voltage, the change in voltage, is 0 because it's an equipotential surface. So that's why if this is 0, this will be 0. Okay, so now let's start with our lovely formula sheet. Let's see, is question 2 also like this? Okay, let's start with the formula sheet. So I'm just going to write them down, all of them, and I'm going to cut to, when they're all there. Before I continue, there's a few more characteristics about equipotential surfaces that I want to give you. Again, I'm going to write them down one by one. There's 2, okay? There's 4. Alright, so these are the 4 characteristics again of properties of an equipotential surface. You must memorize them because he loves to get these select all that apply questions, and I really see it coming. Honestly, I see it coming, especially since we've done no CA on this topic yet. Okay, so equipotential surfaces do not cross or touch. They are smooth, they are perpendicular to the electric field lines, okay, and they are denser near the charge. Okay, now let's say when do you get an equipotential surface? Like a nice thing to remember, when all charges stop moving, or they're at rest, or something like that. Or you can say when they're at rest or they stop moving, the conductor or the surface becomes equipotential. Alright, that's the idea. Okay, these notes I gave you, please memorize them. Hafiz. Okay, now we start with the formula. Alright, so I wrote down all the formulas. Let's start. First formula, very simple. Basically, if you're moving a charge from one point to another, you need to understand that there's always work being done. Alright, that's the main thing. Now, over here, when you're moving from point A to point B and there's work being done, the change in electric potential energy is always equal to the negative of the work. Alright, so these two are related like this. Now, let's say you have 2 charges and you want to find the electric potential energy between those 2 charges, very similar to the electric field formula, which was KQ1 Q2 over R squared. Here it's the same thing, but without the squared. Alright, that's for 2 charges. Now, over here, you're gonna see me, now I wrote it on the side, you're gonna see me switching like a lot, like both work, or I write down or a lot of times, because I swap K with 4 pi epsilon node, because these are the same thing. K is 9 times 10 to the power of 9, 4 pi epsilon node is also 9 times 10 to the power of 9. Alright, so you may see both of these formulas. Alright, this is more common. Okay, the 4 pi epsilon node is, you'll see it a lot. Okay, anyway, so for 2 charges this is the formula. Same thing, but like literally I just swapped K with the 4 pi epsilon node. Now let's say you have many charges and you want to find the electric potential energy. Same thing, you always have the stationary charge Q1, okay, and then inside the Q2 over R, if there's many, it's going to be KQ1, which is your stationary charge. Remember, the K stays there, but instead of Q2 we have Q2 over R2, and then there's more charges, Q3 over R3, Q4 over R4. Same thing here, you have your stationary charge always, but instead of K, I swap the K now with the 4 pi epsilon node. Alright, let's continue. Over here, V is equal, what's happening? Yo, where my mouse speaking? Alright, V is equal to U over Q. Again, very easy formula. This is also derived from W is equal to QV. Very similar to it, okay? Because energy is energy at the end of the day. So V is equal to U over Q. Now, VAB, which is VA minus VB, is equal to W over Q. Now, some people may see this and get so confused, but just remember W is equal to QV. This is the same thing. It's the same formula. W is equal to QV. But you just rearrange it. If you take Q to the other side, you're going to get V is equal to W divided by the Q. V is equal W divided by Q. Now let's say you want to find the electric potential. I want you to know the difference between electric potential energy and just electric potential, balal energy. You're going to see both these terminologies a lot. Electric potential يعني voltage. Electric potential energy يعني U. You're looking for the actual energy. هون لما بقول لك V, I'm not telling you voltage, I'm gonna tell you electric potential because I want you to get used to it, okay? They call the V electric potential, not electric potential energy, electric potential, okay? And from one charge is basically KQ over R, or again, swap the K with the 4 pi epsilon node, you get Q over 4 pi epsilon node R. Let's say you have many charges. If you have many charges, similar to how we did it for the potential energy, same thing, instead of the Q, you're gonna have Q1 over R1, Q2 over R2, Q3 over R3. And again, I put two formulas because instead of K, I put 4 pi epsilon. Now, this one you may think is not important, but I saw it in my prep list and that basically means you could see it in the exam, so I don't want to make any promises. For a large continuous distribution of charge, K integral dq over R, or 1 over 4 pi epsilon node integral dq over R. Now, again, better to memorize the second ones, the one with 4 pi epsilon node, okay? So this one I'd rather you memorize. Now, if the electric field function is given, so let's say they tell you find the electric potential knowing that the electric field is given to 7x squared plus whatever, all you have to do is use this formula over here. If the electric field function is given, the electric potential will be the integral of the electric field cos theta dl from A to B. Alright, so easy. The last one, which is the most important one out of them all, is V is equal to E times D. This one is used a lot. Okay, so many times you're gonna see this formula. Right. Now that we know our formulas, we should well be able to solve. Let's start. Question 2. A positive charge of 4 microcoulombs, so we have Q, is moved through an electric field where the potential is 250 volts higher than before. So they gave us V. And the increase in the potential energy of the system is what? So they want what? U. What was the formula? V is equal to U divided by Q. صح? Let's see. What's V? 250. U is, we don't know, we're trying to find. Q, 4 times 10 to the negative 6. Let's cross multiply. One times 10 to the minus 3, so since it's 10 to the negative 3, you can simply say 1 millijoule. As they're saying milli, so you multiply your answer by 1000. You get 1. So easy. Question 3. The total electric potential at a point denoted by P is 2 kilovolts. So they gave you the V. The work required to bring a 6 microcoulomb point charge from infinity to P is how much? Okay. 6 microcoulombs and Q. Well, they want to find the work. Okay. We know that W is simply, when you have V and Q, it's Q times V. Alright, the work done from A to B. Anyway, so it's going to be Q, which is 6 times 10 to the negative 6 times 2 times 10 to the negative, times 10 to the power of 3. Very easy. It can't get easier than this. You get 0.012, but they want it in millijoules, so multiply by 1000. You got 12. So far so good. I hope I'm recording. Yes I am, alhamdulillah. Yeah, let's continue. Alright, over here, this is a bit new. A proton of charge this, so they gave us Q, is released from rest in a uniform electric field E. So they gave us E, nice. Directed along the positive x-axis, the proton undergoes a displacement of this. So they give us the distance, and they want the change in the electric potential energy of the proton. One second, I need to sneeze it up. Alright, so they want the change in the potential energy of the proton, so they want U electric, okay? Now when they say change in electric potential energy, and they want delta U. Okay, now what formula do we know for delta U? Always remember this one here, delta U. Don't use this, because this is at a certain point. At a certain point. Okay? On certain point. But on, we're moving. Okay, when you're moving, you can't use that. We're gonna use which one? We're gonna know that from any point A to B, when you're moving, the change in potential energy is gonna be equal to the negative of the work. Now, what do we know about the work? We know that the work is equal to Q times V. So, can we figure out Q times V over here? We know that delta U is equal to negative of the work done from a point A to point B. صح? طيب, we know that this is just Q times V, so negative Q times V. So we have a small problem. عندنا the Q, but we don't have the V. But what did they give us? They gave us the distance, or they gave us the electric field. Remember that V is equal to E times D. Let's say you didn't know this in the exam. Here's a nice trick to help you remember. If you look at the unit of the electric field is volt per meter. So they're telling you that this electric field is equal to the voltage divided by the meter strength divided by the distance. So they're giving you the formula pretty much from the unit you can get the formula. Anyway, so that means V is equal to ED, which is aslan the formula that I wrote for you over here, number 10. I wrote it for you. Okay? And that means it's gonna be 7.5 times 10 to the power of 4 with distance E 0.6. So you get 45,000 for the voltage. So voltage is equal to, I'm just gonna say 4.5 times 10 to the power of 4 volts. Okay, so this is your voltage. Cool. Now let's go back here. So the delta U is equal to negative el Q here 1.6 times 10 to the power of negative 19 times the voltage, which is 4.5 times 10 to the power of 4. Let's do it. You get this, wakid, it's negative, huh? I forgot to put the negative. So you get negative 7.2 times 10 to the power of negative 15. So easy. Question 5. A point charge Q1 is held, this is the charge, is held stationary at the origin of coordinate system. So this is the stationary charge. When they're telling you a point charge, that means that's the Q1, that's the one that's stationary. If you recall, in some of these formulas, I'd have one charge that always stays outside. That's the stationary charge, okay? Anyway, so they told us, cool, that it's held stationary, and then the second point charge, this is moved from this point to this point. What's the work done by the electric force to move it from A to B to 2 decimal places? Alright. So this is the continuation of the quiz, because I was falling asleep last time I solved this, and صراحة now I feel like I'm gonna fall asleep, but yalla, we're gonna solve. So we're continuing here from question 5. So over here you have a charge Q1 that's being held stationary at the origin of a coordinate system. They give you a second point charge Q2, which is moving from point A to point B. Alright, so they're basically asking you to find the work done by the electric force to move it from A to B. Now, whenever you have two charges, when they're telling you held stationary, there's work being done, that means we're talking about there's some sort of energy, right? Anytime you see work being done, remember you can always relate work being done to the negative change in potential energy. So simply we can find the work if we find the change in potential energy. Now the change in potential energy is nothing but U final minus U initial, right? So basically we can find the U at B and the U at A, subtract them with each other to get delta U, and just make that value negative. So let's find UB. Remember that U electric as a result of 2 points is KQ1 Q2 over R. So UB will be K 9 times 10 9 Q1, which is 1.5 times 10 minus 6, Q2, which is negative 4.5 times 10 minus 6, all over the first r. Now at the point here, we're starting, here we're finding b, ub. If we're finding ub, yani the distance r, the distance will be over here at point b. What's the distance if you're at 0.25, 0.25? What's the distance? When I say distance, yani I'm looking for the magnitude of the vector. This vector is 0.25, 0.25, so that means the magnitude of it will be 0.25 squared plus 0.25 squared. You get radical 2 over 4. So over here, I'm going to put over radical 2 over 4. How about UA? Same formula, KQ1 Q2 over R. So 9 times 10 to the power of 9 times Q1, which is 1.5 times 10 minus 6, times Q2, which is this, all over the distance at A. And at A, the distance is just simply 0.5. Now, what the idea is, U final minus U initial. Yani when you subtract these two, you're gonna get the work done. Okay? So, U final is at point B. So, this here, minus this, will get you delta U. But, we need it to be negative delta U. So, negative delta U. So, when you subtract this by this, you're gonna get what's called delta U, but you just need to make that answer negative. So when you get this, you're gonna get 0.05, then making it negative, you're gonna get negative 0.05 joules. Alright, moving on to the next question. Oh my god, while I'm falling asleep, I'm falling asleep, I paused the recording. If you go back, I think I paused it at like 6:30 something. Walla, it's 48. Walla, أنا مش عايشة قدامي bro. Anyways, an electron of mass this has an initial speed of this. The electron moves parallel to the x-axis and its speed is reduced to this at point A. The potential difference VAO of point A, relative to the origin O to 1 decimal place is what? Now this is actually very easy once you think about it. So they gave you the mass and they gave you velocity, and then they gave you mass and the final velocity. Well, they're asking you to find the potential difference. Alright, always remember that potential difference has many formulas, but when you're talking about mass and velocity, always think about kinetic energy when you have mass and velocity. Now, how can you rate velocity, how can you rate potential difference V, the voltage? How can you rate voltage to any energy? Remember that work is equal to QV, right? So that makes everything way easier. And I think you guys are familiar with the conservation of mechanical energy. ME1 plus work external equals ME2, right? Now this is kinetic energy, so it's part of the mechanical energy because it's moving. So we could say K1 plus the work done equals K2. So let's do it. Half M, I'm gonna put M because it's a big number, okay, times V squared, so 3 times 10 to the power of 6 squared, plus work external, which is Q V, equals K2, which is half M 2.1 times 10 to the power of 5 squared. Now, why are we doing this? Because whenever you see mass and speed and you're working with electricity, always think mass and speed, and we're talking about kinetic energy, okay? So you follow this step here. Alright, other people use, instead of this, the work energy theorem, that work is equal to the change in kinetic energy. You can use this as well, but I prefer using this. Alright, anyway, since it's an electron, you're supposed to have the charge of an electron memorized, so it's going to be half M 3 times 10 to the power of 6 squared plus 1.6 times 10 to the power of negative 19. It should be negative because the charge of an electron is negative, times V, right? Q, this is Q, this is V, equals half M 2.1 times 10 to the power of 5 squared. Now just substitute the mass here and you can solve for V. Very easy. Question 7. You have a proton of mass this and charge this accelerated from rest through a potential difference of 105. They want the final speed of the proton. Again, same thing, by the way. whenever you're talking about speed and mass, they want you to use conservation of energy, something to do with kinetic energies and like all the energies. So ME1 plus the work external is equal to ME2. Since ME1 starting from rest, K1 is 0, plus the work external, which we know W is just QV, equals ME2, so kinetic energy final, or kinetic energy 2. Anyway, Q, since we know it's a proton, they gave us the charge aslan. The voltage they gave it to us 105. K2, very easy, half times the mass, which is, I'm just gonna keep it as M, times the velocity squared. Right? Now this M, you know it, I'm just writing M because it's a long number. Okay, so now solving for V should get you 142,000. Let's see. So you get 1.6 times 10 minus 19 times 105 times 2 divided by this mass, and then square root this, you get this. Now they want it in kilometers per second, so you divide by 1000, and you get 142 to 3 significant figures, 142. Okay, very easy. Over here, consider two charges, Q 6 microcoulomb and Q prime equals negative 6, found respectively at these points over here. A certain surface S is equidistant between the two charges. Okay. The electric potential at any point along S is equal to 0, and the surface is called equipotential. Why? Because Heidi, it's two oppositely charged particles. You have a surface that's also equidistant. So if you have charge here which is 6, one negative 6, we have one that's equally distant between them, the potentials will cancel out left and right. So that's why we say that the electric potential at any point here will be 0. And obviously the surface is called equipotential. Now another note, if you have an equipotential surface and you added voltage from any side, since it's equipotential, those are going to cancel out. So there's an important note to memorize, that the addition of any kq over r, or any charge that you want to, or any voltage that you want to add, will just tend to 0. It's going to cause a 0 because what they keep on cancelling out. Alright, the electric potential 2 meters away from a positive point charge of 3 nanocoulombs to the nearest integer is something. Now electric potential means بدون voltage. They gave you the distance, or they gave you the q, or sorry, you could say this is the r, and this is k. Very easy. V is equal to kq over r. So simply this times this divided by this. No need to solve, so easy. But I'll just make sure. 9 times 10 to the power 9. 3 times 10 to the minus 9 divided by 2. You get 13.5 to the nearest integer, which would be 14. Yes. Q10, two charges of 2 and 6 are separated by distance of this. Given K is this, what's the electric potential energy? We know this. U electric is K, Q1, Q2 over R. So 9 times 10, 9, times 2 times 10 minus 6, times 6 times 10 minus 6, over 0.04. You get this. Question 11. The electric field between two parallel charged plates is uniform and is equal to 500 newtons per coulombs. 3 points A, B, and C, as you can see here, are taken in the space between those two plates. AC is perpendicular to the plates and equal to 12 centimeters. BC is okay, they're basically giving us the given. It's all in the drawing. What's the potential difference between points A and point B? So here, this is very easy. Okay, all you need to know, how do you relate potential difference? The concept even says it. But you want to find potential difference. Anytime, keep this in mind, okay? I want you to take, learn proper ways of solving and thinking. Anytime you have potential difference where there's an electric field, use the formula V is equal to ED. This is the potential difference. Anytime you have distances, use this formula V is equal to ED. Now here's the problem. Between points A and B, the electric field is 500. Nice. How about the distance? The distance, do we take it as 13? No. Why? Because the electric field doesn't go like this. No, the electric field goes horizontally. But since the electric field goes horizontally, you need to know that the distance you choose here is not this 13. It's actually the 12. So it's going to be 500 times 0.12, because it must be in meters, and you're going to get 60. I like Q12. A proton of mass this is released from rest in a uniform electric field. The change in the potential energy is this. They obviously ask you for the work. This is a good question, by the way. What is the work done? If you're ever given the change in potential energy, to find the work done, it's so simple, you just make it negative, okay? So work is equal to negative change in potential energy, okay? last one. كده كام سؤال احنا عندنا؟ Oh my god, 18. Oh my days. Alright, so over here, a proton of charge, this is released from rest in a uniform electric field. Yeah, well basically, the electric field has this magnitude, and the proton undergoes the displacement of this in the opposite direction of E. So we solved a very similar question earlier. What is the change in the potential energy? Now, change in potential energy, and looking for delta UE. With the only thing that includes delta UE, the only formula is delta UE is equal to negative W done from 2 points. Now, can we relate this W to anything that we have here? Here we have Q, we have E, and we have D. Alright? Now, we know that the only formula that we know about W is that W is equal to Q times V. But we don't have V, we have E and D. We know that V is equal to ED. Right? So, just like that, we started with one thing, we ended up with another. So, we now need to find negative W done from A to B to find the change in U. Now, negative work done from A to B is just negative Q times V, which I told you is ED. Alright, so it's going to be negative 1.6 times 10 minus 19 times 5 times 10 to the power of 3 with distance 0.5. Do it till you get this, okay? Very easy, so easy, so easy. I'm going to go next, okay? The rest of this quiz is very easy, so I'm going to go a bit faster because I have to go. Alright, over here they gave the distance between two plates is 0.10, so this is D. With the electric field strength is 5, so this is E. Well, they want you the potential difference V. Sorry. So it's very easy. V is equal to E times D. So simple. You do 5 times 0.1, you get 0.5. Someone might ask you, why do you convert the units? Because here it's centimeter, or here it's over centimeter, so they can just cancel each other. Okay? But in the exam, don't do that. Actually do it. So here you divide by 100. Here you multiply by 100. Someone might say, why you multiply by 100? Because it's voltage over centimeters. So the centimeters is the denominator, so you do the opposite. So instead of dividing, you'd multiply by 100. Alright? Anyway, question 15. During a lightning storm, the distance between the clouds is whatever. So this is D, 1 kilometers. Basically, lightning strikes the ground. Ooh, this is the Q that falls. Alright, knowing the electric field strength between the clouds is this. So this is E. How much work is done by the electric field? So work, we know is Q times V. But unfortunately, we don't have V, but they gave us the E and they gave us the D. So W is equal to Q times ED. ويعني الQ قد ايه؟ الQ is 19. But we take it to be positive. ليه؟ لأنه we're going from... Sorry, we take it to be negative. But I'll tell you why the answer is positive in a sec, okay? E is 1.5 times 10 to the power of 6. D here 1 kilometer, which is 1000 meters. But why is the answer positive? لأنه you're moving from the clouds to the ground. This is an increase in work. Work done is positive here. Work done is... the work done, is negative. For a proton. For a positive charge. So when it's negative, you gotta know you're falling down, which is negative, as well as it's a negative charge, so negative becomes positive, okay? So negative of all of this gets you the positive answer, which is over here. Alright, very easy. If you're getting the same example in the exam of the lightning striking, just keep it positive, okay? Unless they tell you that it's a positive charge instead of a negative charge. Anyway, 4-point objects, each charged to 8 microcoulombs, are placed at the vertices. Basically, you have a couple of charges around 1 point, and they're asking you to find the electric potential. Again, I want to stress on electric potential. They didn't say electric potential energy, they said only electric potential. When you say electric potential, that means you're saying V. Okay? V, you have a lot of charges. What formula do we use? It's right here. Oh, tell me I lost it. No, it's here, okay. over here. For voltage, if you want to find electric potential, there's a lot of charges. It's simply K, Q1 over R1, Q2 over R2, Q3 over R3. So let's do it. This is point P. So V is equal to K into Q1 over R1 plus Q2 over R2 plus Q3 over R3 plus Q4 over R4. صح؟ طب nice. انت هلا Q1 is over here, over here, over here, over here, yeah, so on and so forth, yeah. So this is Q1. They're all the same charge, so I'm just gonna find it once. They're all the same distance as well, so I'm not gonna do it 4 times because I'm very lazy. I'm just gonna multiply and do it once and multiply it by 4, which is the same thing. Okay. Anyway, so what's Q1 over R1? Q1 over R1 is this: 8 times 10 to the negative 6. With the distance between this point here and the charge, is very easy to calculate. Actually, it's so easy. All you have to do is take this. This is 5. Well, this is 5. So calculating the length of the hypotenuse will just be 5 radical 2. Do it if you want. 5 squared plus 5 squared, then square root. You get 5 radical 2. So I only want from the point to the charge, so not the whole thing. This is going to be half. So this is going to be 2.5 radical 2. Why? Because half of 5 is 2.5. So 2.5 radical 2. If you're in 12S and you don't know how to calculate the Pythagoras theorem, you don't know how to calculate the hypotenuse, يعني هون هيدي 2.5 وهيدي the height of it is 2.5. If you don't know how to calculate this distance, يعني I'm sorry, والله I think there's grade 7s who know how to do it. Okay. Anyways, you get that this distance is 2.5 radical 2, but أكيد it's centimeters, so we have to divide by 100. Okay. Anyway, so we're gonna multiply this by 4, and this is gonna be all of this, and then أكيد multiplied by K. So K, Q1 over R1, Q2 over R2, Q3 over R3, Q4 over R4. Since they're all the same charge and same distance, we're just gonna multiply this by 4. Okay. So 9 times 10 to the power of 9 times 4 times Q1 over R1, which is 8 times 10 to the negative 6 over 2.5 radical 2 divided by 100. You get like a really big number. They want times 10 to the 6, so let's just click on the scientific notation button, and you get 8 times 10 to the power of 6 to the nearest integer. Okay, to the nearest integer. Nearest integer. Okay, so it's here 8 times 10 to the 6. Okay, Q17, we're almost done. Q17 is also very easy. Okay, over here basically you have like a setup here. You have Q1 and Q2. They told us that Q1, the charge of Q1 is Q, so we're just gonna call this Q. The charge of Q2 is 2Q, so we're gonna put 2Q over here. Cool. They said the electric potential at point A is called V. Okay, what would be the new electric potential if the first sphere is changed to 2Q1 or the second sphere is changed to 4Q2? Now, what people think, they say, oh, times 2 times 4, so we're gonna put 8V. No, that's not the formula. The formula for V, for the voltage, for the electric potential, they're saying the new electric potential, so they're asking about voltage. The formula is not Q1 times Q2. The formula is K, Q1 over R1 plus Q2 over R2, and so on and so forth. But here we only have 2 particles, so it's just Q1 and Q2, right? Type, let's find what you have to do for these types of questions. When you have new and old, you need to calculate what old is and what new is, and then divide them by each other. V old will be K, Q1 over R1 plus Q2 over R2. Now, obviously K is just 9 times 10 to the power of 9. I'm just going to keep it as K, okay? Q1 is Q, right? Over R1, which they gave it to us as D, plus Q2, which is 2Q, over R2, which is also given to us as D. Now, we're going to common denominator. This D and D is already common denominator, so we can add these up. You're going to get K into 3Q over D. So this is V old. Let's find V new. V new, again, same formula, KQ1 over R1 plus K2 over R2. So K, I'm going to leave it as K. Q1 now became 2 times Q1. So 2 times Q1. And then how much was Q1? Q1 was equal to Q, so it's going to be 2 times Q. So instead of Q1, we're going to put 2Q over R1, which is still D. They didn't do anything to the distance. Plus Q2. Q2 now became 4 times the old one. The old one, 4 times Q2. The old Q2 was 2Q. So it's now 4 times 2Q. So start 8Q. Okay, so 2Q plus 8Q divided by R2, which is the distance D. So it's K times 10Q, 10Q over D. How do we compare these two? We divide V new by V old to see what the difference is, yeah? So K into 10Q over D over K into 3Q over D. Loop, loop, cancel, cancel. D with D, Q with Q. You're left with 10 over 3. So what did you have to multiply the old one by to get the new one? 10 over 3. So V old equals 10 over 3. Sorry, V new equals 10 over 3. V old. Nice and easy. So 10 over 3. Okay. Last question, question 18, very easy. They gave you A, B, C, D, and they're asking you which one has the strongest magnitude of electric field. Actually, it's the one where the lines are closest together. Over here, you can see these lines are very close together. Okay, so that's gonna be the answer. Okay, so point A. Thank you so much for watching, and good luck in your exam.